Hello, my name is Auruba Islam, and I'm joined today by my team members, Grace Desmond and Ahmed Isse, for our senior design project presentation, Team Portable Oscilloscope. The goal of our project is to design and develop a portable oscilloscope that will be handheld and it can measure analog signals for field use without having to rely on computers or any lab setups. It will be battery powered with a color display and it can differentiate up to two input channels. The maximum voltage per channel will be 30 volts. It will have data storage options on removable medium of SD card. It will have a user-friendly design with minimum controls and easy operation. We are aiming to deliver a refined field-ready product for immediate use. And I will hand it over to my team member Ahmed to talk about the front end part of the oscilloscope.
Hello, and we're looking at a high-performance analog front end, the kind you would find in precision measurement equipment like oscilloscopes, where capturing signals accurately without affecting the source is crucial. Our design is based on the open source Thunderscope, where the signal arrives via the BNC connector and immediately encounters the ESD protection. The circuit presents a high 1 mega ohm input impedance to avoid loading the device under test. Following this, a 50x attenuator network scales down the large input voltage, which in our case is between positive 30 volts and negative 30 volts, greatly extending the visible input range of the instrument. A key element is the composite loop buffer. It uses two parts, the buff 802 chosen for its high speed and OPA 140 selected for DC precision and low input current. Working together in loop, they provide both the bandwidth needed for fast signals and accuracy needed for DC levels. Next is the AD8336 variable gain amplifier, VGA, which adjusts the signal amplitude, which adjusts the signal's gain. This electronic control allows the system to optimize the signal level, make sure it properly fits in the input range of our next stage, which is an LTA 15068, which is a low pass filter. This stage serves to remove unwanted high frequency noise and performs critical anti-aliasing, prevent distortion if the signal is later digitized. So I leave this my statements to Grace. I leave the rest to Grace.
So this is our display. We are using the Reverity STM32 H757 display. So it features a H757 on the back of it. We are programming it through the ST link of the discovery board, but this will not be a part of the final project. It's currently being powered with a 12-volt power supply, but that will later be replaced with a battery. There are currently two 1 Hertz waveforms applied on the ADC pins, and the ADCs are sampling it and displaying it here. For reference, these waveforms are also being displayed on the oscilloscope, and you can see that they are pretty in sync. To show it is 1 Hertz here, and to show the more easy to read, we will look at the poster. Here you can see that the period is 1 second, which is shown on the bottom. And so the STM ADC is accurately reading the data. The markers and cursors will be programmed along with a user interface, and the ADCs will be programmed faster using the DMA, but that has proven challenging. I'll hand it over to Auruba to talk about the battery.
Our device will be powered by a LiPo battery rated at 1300 mAh of 22.2 volts so that it can be powering the device for extended periods of time in the field. Our device will also be enclosed in a housing that has the dimensions 12 by 8 by 6 inches. Our priorities are the internal spacing, the mounting and routing of all of the components within the enclosure. Our immediate next steps is to design a PCB board such that we can trial the initial schematic design and finally order it from the manufacturer for the final prototype that we will achieve by the end of this month. Thank you.